Welcome to the 39th class in this course, the physics of materials. In the last several classes that we have seen, we have often encountered various particles and tried to understand what their behavior is, what it represents in terms of material behavior. So throughout this course, at several occasions, we ran into the photons. Okay, so those are the particles of light, so to speak. When light indicates its behavior in the form of particles, we call them as photons. We also looked at vibrations in the lattice and said that those are waves, but you could also look at them as particles because the manner in which they interact with respect to energy, the way they pick up energy, the way they lose energy, that is also still quantized, and so in a sense they behave like particles. Those particles of lattice waves are referred to as phonons. And in the last class we looked at a particular combination of particles, which basically we said that pairs of electrons with opposite spin and opposite wave vectors could combine together and operate in a coordinated manner, and in that sense would behave like a combined particle, so to speak, although they are quite far off from each other, but their behavior would appear like that, and those would be called the Cooper pairs. Okay, so we saw these, so this is what we saw last class, and so these are all the are some of the particles that we have seen through the course. As it turns out, and as I mentioned in the last class, all of these have characteristics that are common to them, and which makes them a certain type of particle, which is called a boson. Okay, so this is a boson, each of them is a boson, and one of the requirements for the particle to be a boson is that it has to have integer spin. So an electron by itself has half integer spin. Okay, so half we say plus or minus half, spin is plus or minus half we say, so it has half integer spin, and therefore by itself it would actually qualify as a fermion. So a Fermi-Dirac statistics is what it would follow. But Cooper pairs, for example, to the extent that they behave as a combined entity, they are actually having a net spin of 0, and therefore it now suddenly shows you an integer spin, and therefore it satisfies the requirement for it being a boson, and so do phonons and photons. So they have integer spin, so they satisfy the criterion for being a boson. So so this is what they are. We have already seen these three. I also mentioned that, for example, when I spoke about the use of superconductors and the fact that they are used often in these particle accelerator and colliders, so to speak, particle colliders, then we have even there, for example, at CERN they are using effectively superconductors which use phonons as well as Cooper pairs, and therefore are two bosons, and they are searching for another boson called the Higgs boson. So at the time of recording these lectures, that is what is being done. So it is of interest, therefore, since we have discussed these in detail, to see what is a boson, what is that behavior that characterizes a boson, what is the distribution, because we always say when you look at a set of particles, we would like to know in terms of energy how are those particles distributed, because that gives you a very good feel for what will that a system of such particles do when they are subject to a certain condition. Okay, so that is why we need these kinds of information. Bosons, they get their name because they are credited to Bose, Satyendranath Bose, who first proposed this, and essentially they follow a statistical distribution referred to as the Bose-Einstein Statistics. Okay, so they follow Bose-Einstein Statistics, and so and hence the name bosons. So today we will look at Bose-Einstein Statistics. So that is our topic for today. Basically, for one of the requirements for Bose-Einstein Statistics is we are dealing with a set of particles which are showing us quantum mechanical behavior, but in the specific case of Bose-Einstein Statistics, it applies to a set of particles which are not subject to the Pauli's exclusion principle. Okay, so the particles are not subject Okay, so these are particles that are not subject to the Pauli's exclusion principle. They are quantum mechanical in their behavior, but they are not subject to the Pauli's exclusion principle. This is very important because when we did the Fermi-Dirac statistical distribution, this was the main principle that we incorporated. We had the Pauli's exclusion principle there. Okay, so it is in this fundamental sense that this distribution differs from what we are doing for the Fermi-Dirac distribution. So it exempts the particles from Pauli's exclusion principle, and when we say it exempts it, we are basically talking of particles which don't care, I mean which are not affected by the Pauli's exclusion principle. So that is why the statistics which is based on this idea works for that those sets of particles. Okay, so they are not subject to the Pauli's exclusion principle, meaning they are exempt from the Pauli's exclusion principle. The direct result of this is that, see, when we say Pauli's exclusion principle, the idea that it reduces to is that you cannot have more than one particle in a quantum state. Okay, once you define all the quantum numbers, finally when you pick up a particular state, which if it includes, if that definition of the state includes the spin of the state and so on, if you put particles in there, you cannot put more than one particle per state. That is the definition of I mean that is what it reduces to when you say Pauli's exclusion principle. That is what it in terms of how you will enforce it in the system, that is the rule that you will use to enforce it in the system. Now when you say that a system is not subject to Pauli's exclusion principle, it means immediately this restriction is no longer true. It means in a given state you can put as many particles as you wish. Okay, so that's the big difference. Whereas previously you could put only one particle per state, now you can put as many particles as you wish in the state, because they are not subject to the Pauli's exclusion principle. Okay, so this is the general idea. On this basis we will do the statistical distribution and see what kind of a result we get. So again we have a system where we have energy levels. So we let us say that the energy levels are quantized. So you have energy levels E1, E2, E3, E4 and so on. So some up to some ER, and let us say it has a certain, each of them has certain number of states. So S1, S2, S3, S4 and so on, SR. Okay, so these are fixed for the system. Given the system, it has certain set of energy levels and certain set of states. Okay, so again this is a constant volume system and so on. We are at an equilibrium. That is what we are looking at. Now we would like to know. We will say that upfront we do not know, but we will say that perhaps there are n1 particles at energy level E1, given that these are the states, n2 at energy level E2, n3 at energy level E3, n4 at energy level E4 and so on, with the total number of particles being n and the total amount of energy being capital E. Okay, so the total energy is fixed at capital E. These are the energy states that are available, and the total number of particles is fixed at capital N. These are this is the way in which that capital N particles has been distributed across all these energy levels. We have n1, n2, n3, n4 at those respective energy values. Now our problem, of course, as we have done before, is to find out what is the relationship that helps us figure out what is the value of n1, what is the value of n2, what is the value of n3 and so on. We do not know upfront what these values are. We would like to find out what these values are, given that the system is subject to the rules that we have just described. Okay, and again these two are fixed. This is the one that we have freedom to change, subject to this restriction that the total number is n. Right. So given this scenario, what we are interested in actually finding out is the effectively the information we are interested in finding out is the probability of occupancy of a state. At energy level EI. Okay. So I said that we really want to know what are these numbers. Mathematically it reduces to this: you want to find out what is the probability that a particular state at any given energy level is occupied. If you have a general expression for that probability, that in fact effectively will sort of give you all this information that we are interested in. So then you can go to any energy level, you can get an idea of what the n is at that level, because that will give you, because we know this, so we have some probability of occupancy and we can sort of figure it out from there. Okay, so we would like to get probability of occupancy of a state at energy level EI. So if you take any energy level EI, we basically have S1 states and N1 particles. I am sorry, Si states and Ni particles at energy level EI, right. So actually the probability of occupancy of a state is simply Ni by Si. Okay, so this is all this is the probability of, you have Si states, you have Ni particles, so what is the chances that a particular state at this one of these states is occupied? It is simply Ni by Si. So this is all we are interested in. So actually, so the problem actually reduces to finding out an expression for this. We want an expression for this based on the conditions that are imposed on the system. So this is the expression we are interested in. Once we get an expression for this, we sort of have the answer for the information that we are looking for. Okay, so that is all we are going to try and do in this class. Now so let us get on to the mathematics of how we go about it. What we will do is we are now faced with a slightly different situation than what we have dealt with before, and that is simply that since Pauli's exclusion principle does not apply, any number of particles could be sitting at a given state. Okay, so therefore what we actually have is we have S1 states and N1 Si states and Ni particles, and really you can mix them up in any which way you want at a given energy level Ei. Okay, so there, since any number of them could sit in one particular state, there is we are free to mix them up in any which way that you wish. So we will just put down here, we have, let us say, Ni particles, which I will mark as x with small x's here, and then we have some states, some arbitrary number of states we have. These are the particles, these are the states. We would like to put these particles into these states in any which way that you want. Now in general, if you have so you have what is this mathematically? You have Si items of one kind and Ni items of another kind. What is the ways in which you can mix these two up? That is in how many ways can you arrange these, given that you have Si items of one kind and Ni items of another kind. Normally when you write such a problem, when you have A items of one kind and B items of another kind, and you would like to know in how many ways you can arrange these these two, the general answer is actually A plus B factorial by A factorial times B factorial. This is the general answer for this kind of a problem. The only issue with this kind of an answer, so in principle we can apply this kind of an answer here, but there is one small detail that we have to address before we do this kind of an we apply it, and that is when you do this kind of a problem, you are permitted to have a situation where you have all the A items first. So let us say A items, so all the A items, so let us say they are squares, A squares, so we can have all the squares, okay, and let us say B is a triangle, okay, so we can have all the triangles after this. This is a valid arrangement as far as this kind of a mathematical problem is there. You can put all the squares first and then all the triangles next. Similarly you can put all the triangles first followed by all the squares. Okay, so this is allowed under this under the problem that we have defined like this in the mathematical sense. Okay, and so this is those are two arrangements that are included in this condition that you are looking at. Okay, now in the condition that we are looking at, we have particles and we have states. If you have this kind of a situation here, it is the same as saying you will have all the particles first and then all the states, or you will have all the states first and then all the particles. That creates a situation that that corresponds to what? It corresponds to a situation where all the particles are outside all of the states. Okay, so that is not a situation that is acceptable for us. All the particles are free to be in any state they wish, but they have to be in some state. You cannot have so this is not a valid condition to have all the particles outside all of the states. Like this kind of an arrangement is not acceptable here. Okay, so we cannot simply write we cannot use this equation in exactly this form. You cannot simply say A plus B factorial by A factorial plus times B factorial. In this case you cannot simply say Si plus Ni factorial by Si factorial times Ni factorial. You cannot do that, because that would imply that you are allowing this system, this possibility that all the particles are outside or several particles are outside. That is not allowed. All the particles have to be somewhere in those states. So how do we do that? How do we handle that situation? A simple way to do that is to say that we will actually treat it as we will eliminate one state in our count. So how many ever states are there, we will take one less state, and then we will arrange all the particles in the remaining states using the same kind of a formula. then whenever we say that all the particles are before or after, it simply means they are in the last state or in the first state, okay. So or alternately, if you have, let us say for example you have here 1 2 3 4 5 states you have here, okay. If you look at it, the number of partitions between these states is 1 2 3 and 4. So how many ever states you have that many minus 1 partitions. So we can treat the problem as though you are trying to arrange Si minus 1 partitions and Ni particles in any which way that you can. If you treat it as Si minus 1 partitions, you will never have a situation where all the particles are outside the states, because if all the partitions occur before the particles, then you have all the particles sitting in this last state, because all the 4 partitions are before all the particles, right. If the other example that we have is all the 4 partitions are in the end, the particles are before that all the 4 partitions, so therefore they are in the first state. So you can now not worry about this situation that we just described. The particles will never be outside these states, they will be stuck within these states, and regardless of what possibility you look at, you can always come back to this picture and you can see that they are either in the first state or in the last state or in some of the states in the middle. So therefore that issue is addressed. So instead of directly just using Si and Ni, which can create this kind of a controversy, we will use Si minus 1 and Ni, okay. So if you use that, all the possibilities are addressed reasonably, okay. So we will do that. So therefore we now have, if you use now this formula, we will have Ni plus Si minus 1 factorial by Ni factorial times Si minus 1 factorial. This we will designate as omega Ni. Okay, so this is the number of ways in which you can attain, you can arrange Ni particles in Si states subject to all the conditions that the Bose-Einstein statistics requires. So this is how we get it, okay. So for the entire system, so this is a for the entire system, the for each energy level you can do this, right. For every energy level, this is only an I. So you for energy 1 you can do it, energy level 1, E1, E2, E3, E4, for every one of them you can do this. So the total number of ways in which you can accomplish a particular microstate, okay. So for that macro state, for example, which we will designate with capital omega. So on particular distribution we have chosen, where this distribution represents n1 at E1, n2 at E2, n3 at E3 and so on. The number of ways you could do that is the product of all these, omega of Ni n1 times omega of n2 times omega of n3 times omega of n4 and so on, for each number of particles at that particular energy level, whatever Ei. So n1 is also at E1, so that is the other thing that we are looking at. So if you write this formula down for every one of those energy levels and their corresponding number of particles and number of states, each of these terms will look like this, and if you multiply all those terms, that's the number of ways in which you can attain that microstate, okay. So that's what we are looking at, okay. So that's the number of ways in which you can attain the microstate. So this is simply, as I using the same notation that we have done before, I equal to 1 to R omega Ni, okay. So this is simply pi over I of this what we have just written. This is omega n bar. So of course, so this is the expression that we have. As we have always stated that for when we use quantum mechanical when we look at statistical mechanical approach of dealing with such problems, which is what we are doing now, the idea is that we would like to find the conditions here which maximize this omega n bar. So that would represent the microstate with the maximum number of ways that it is possible to attain that microstate, okay, and that would then represent the equilibrium state of the system, because as we have discussed before, the most probable state is more probable than all the other states combined. We discussed that in detail before, so we will just accept it now. So that is what we are going to do, okay. So we are going to try and maximize this, and also in general if you look at omega n bar, it is of the form that whether you maximize this or you maximize the log of this, both of them will give you the same result. The two functions are such that ln omega n bar and omega n bar will behave in such a way that when you maximize omega n bar, ln omega n bar maximizes. Similarly, when ln omega n bar reaches a maximum, whatever is that condition, same condition, omega n bar will maximize, and mathematically it is easier to handle ln omega n bar. So that is what we will do. So rewriting it, we have omega n bar is pi over I ni plus Si minus 1 factorial by ni factorial times Si minus 1 factorial. So if you take the ln of this, it is simply, now it becomes a sum. What was a product? Because you have taken natural logarithm of this product, you get it becomes a sum. It is ln ni plus Si minus 1 factorial minus, we can put this under bracket because it is sum over the same I is in for every term, it is the same I, minus ln ni factorial minus ln Si minus 1 factorial. Okay, so this is what we have, and in general what is true is that given the values of ni and Si, ni plus Si is much larger than 1. Okay, in general ni plus Si will be much larger than 1. So ni plus Si minus 1 can be reasonably approximated to ni plus Si, okay, because it is larger than minus 1. The same will not be true for this term, but for this term it will be true. So therefore here we will leave the minus 1, here we will remove the minus 1, because ni is a very large number generally. So ni plus Si minus 1 is simply ni, is simply ni plus Si. So we can do that here. So this is simply that is one thing, one change we will make, plus we will use Stirling's approximation. Which simply says ln of x factorial is x ln x minus x. So for every one of these terms, each is a ln of some factorial. For every one of those terms, we will do this approximation, and we will change this ni plus Si minus 1 to just simply ni plus Si. Okay, so therefore this is simply equal to, we will write that here, ln of so this is ni plus Si the summation is still there. Okay, so the summation is still there, we are only looking at the terms within the bracket, summation over I ni plus Si ln ni plus Si minus ni plus Si. Okay, minus, we can put a bracket here, curly bracket, ni ln ni minus ni plus Si minus 1 ln Si minus 1 minus Si minus 1. Okay, so this is what we have. Now if you look at it, there is a minus ni here and there is a minus of minus ni, so that is a plus ni, so this ni and this ni will cancel. Again there is a minus Si here, there is a minus of minus Si here, so this Si's will cancel. Okay, so they cancel out. So we have just simply used Stirling's approximation to get here and substituted ni plus Si minus 1 as ni plus Si. So those are the changes we have made. The summation is still there, this summation that you see here, that you see up here continues to remain there. So that is what we continue to have here. Okay, so this is what we got, these terms go. So therefore this is so we have the result to be and then a plus 1 will be there. No, you will have a minus of minus, so it is plus minus 1 will be there, a minus 1 there. So there are 3 minuses here, minus, minus and minus, so you have a minus 1 there. So this is the result that we have got. Now as we have always discussed, if you are maximizing this, then effectively the differential of this with respect to Ni, the variable you have here is only Ni. So if you are maximizing this, the differential of this with respect to Ni should be a 0, and we can also write it as simply as del ln Wn bar should be equal to 0, where you are effectively differentiating that with respect to Ni. So everything else is a constant here, Si is a constant, right, and of course 1 is a constant. So now when you differentiate it, this is entirely a constant, 1 is a constant, all of this term is a constant, so this entire thing simply reduces to 0. So we will only have terms coming from the first term and the second term here, this simply disappears, right. So if you write it down, we get so this implies that sigma over I Ni plus Si, let us differentiate this term, so that will be 1 by Ni plus Si times del Ni, because that Ni will be differentiated, that is del Ni, and you can also differentiate the Ni here, so plus del Ni, again Si is a constant, so that goes to 0, times ln Ni plus Si, right. Now you take the second term, again you will have minus Ni by 1 by Ni del Ni, and also minus del Ni ln Ni. So that is this will give you 2 terms because you have 2 Ni's here, and this also gives you 2 terms because you have 2 Ni's. So these are the 4 terms that you get. Of this, if you see again, this reduces to simply plus del Ni, because this will cancel, so that is plus del Ni, and this reduces to minus del Ni, this will cancel, so minus del Ni. So again this entire term will cancel with this entire term, so this is go, so this will go, and so you basically have del ln, so this implies that of course this the fact that this is equal to 0 simply implies whatever we have calculated here equals 0. Okay, so so that simply implies that the summation over I, the only terms that are left are this del Ni of ln Ni plus Si minus ln Ni equals 0, and since it is ln, you can actually simply put that in the denominator. So this implies sigma over I with marginal, and put this just rearranging the terms, we will have or we will write it right at the beginning, del Ni ln Ni plus Si by Ni equals 0. So we have got this combination, we have got simply taking the number of ways in which we can arrange the system and trying to maximize it. We have found this one condition that needs to be satisfied, which we have got as del Ni ln Ni plus Si by Ni equals 0. So we will write that down here. So that is our first equation, sigma over I del Ni times ln of Si plus Ni by Ni equals 0. Okay, so this is the condition that we have got. So this is equation 1. As before, the total energy in the system is conserved and the total number of particles in the system is conserved. Conserved meaning you cannot increase or decrease this, the number of particles is already there, you have no choice in it, it is not going to change. So therefore sum of all the particles sigma over I Ni, okay, so N1 plus N2 plus N3 plus N4 plus N5 etc. equals the total number of particles equals a constant. Okay, therefore if you just differentiate this with respect to Ni, that has to be 0. So that simply means sigma over I del Ni equals 0. That is the same as saying you have a total number of particles, you simply remove a few particles from one state, you distribute it amongst the other states. So what is the change? You remove some particles, so you have reduced, so some minus term comes there, so the change in particles there is some minus 5 particles, let us say, because you removed 5 particles. The same 5 particles you put in like 3 other states, so therefore you have plus 2 and plus 1, let us say. So minus 5 plus 2 plus 2 and plus 1 should give you 0. That is basically all it says. Okay, whatever particles you remove from one state, you have to add to some other state, therefore the sum of all the changes has to be 0. Similarly, the energy is a constant, total energy of the system is a constant, so epsilon I Ni equals constant, which we designated as capital E. Okay. So again here the each energy level in the system is already fixed, you do not have freedom on that, so this is already fixed for you. Okay. So therefore only change that you can do is here. So again the changes in energy that you will do when you remove some particles is the energy level times the number of particles that you remove, and when you add increase energy, when you add it to some other state, it will be the energy of that state times the number of particles that you are adding to it. Okay. So therefore changes in energy, total change in energy is simply sum over I epsilon I del Ni. For all the states, what is the number of particles you are adding or removing times the energy of that state, that gives you the total change in energy with respect to that energy level. Sum of all those changes has to be 0, because the sum of all the energies together is anyway equal to a constant, so this is equal to 0. So we now have 3 equations, we already identified equation 1 here, this is equation 2 and this is equation 3. Okay, so we have 3 equations, and what we will do is effectively as we have done before when we looked at Maxwell-Boltzmann statistics and we also looked at the Fermi-Dirac statistics, what we will do is we will use the Lagrange method of undetermined multipliers and then we will solve this system. So we are going to use the Lagrange method of undetermined multipliers. So we are actually simply going to multiply this by a constant alpha, this by a constant beta, and add it to this equation up here. So that is what is going to be there, and they are all equal to 0, so that sum is also going to be 0. Okay, so that each of them is 0, so it does not matter what you multiply it with, it is going to remain 0, and we are going to add it to this. Only thing is, by convention, because the result works out more convenient to interpret, instead of simply adding to this equation, we add it to we add these two to minus of this equation. Okay, and that is only a convention simply to make the interpretation easier, and in a sense it makes again no difference, because it is anyway it is equal to 0. So whether you put a minus sign in front of it or plus sign in front of it makes no difference. So we will add a minus sign here and then we will add these terms together. Okay. So our when we do this, when we do what I just said, where we are multiplying by 2 constants and adding them, this is what we will get, summation over I. We will write the first term down the same way, minus we will put a bracket here, minus ln Ni plus Si by Ni, this bracket covers everything including the Ni, plus alpha epsilon I am sorry plus alpha plus beta epsilon I del Ni equals 0. Okay, so we had 3 terms, we had sum of epsilon I del Ni equals 0, we have multiplied that by beta and brought it here. We had sum of del Ni equals 0, we have multiplied that by alpha and brought it here, and kept the original equation. So it is equation 1 plus alpha times equation 2 plus beta times equation 3, which is what we have done. Okay, so that is equal to 0, and as we discussed before, the point is we have a bunch of energy levels, we have a bunch of states at those energy levels, and when you maximize it, regardless of what changes you are making in those states, adding a little, subtracting a little, this sum should always be 0. In other words, this sum has to be 0 regardless of the values of these Ni, because you can keep making minor changes here and there, still it should be a 0. So independent, in other words, we have to make it independent of these del Ni. Okay, and the only way you can do that, so therefore the only way you can guarantee that the sum is 0 regardless of where you are adding, what you are adding, what minor changes you are making, the only way you can guarantee that this is 0 is to say that every individual term here within this bracket has to become, I mean this whatever is within the bracket should always be 0. Only when you do that you will be able to guarantee that this sum is equal to 0. So therefore we say ln of this is the term within the bracket. As long as you guarantee that this term is 0 regardless of which energy level you are looking at, EI you are looking at, you can guarantee that the sum remains 0. Okay. Otherwise it is difficult to guarantee because you have all sorts of various values for del Ni, and then it will become difficult to guarantee. This is the only way you can guarantee it 0. So now we have this expression, we will rearrange it marginally. So basically it says that ln of this is Ni plus Si by Ni, so this is, we can simply write it as 1 plus Si by Ni, and we will move the other two terms on the other side. So therefore that is why this minus sign is now suddenly disappeared, is alpha plus beta epsilon I, and marginally and therefore once you simplify it further, 1 plus Si by Ni equals e power alpha plus beta epsilon I, and this implies Si by Ni equals e power alpha plus beta epsilon I minus 1. Okay. We started off by saying we want to know the probability of occupancy of a state at energy level EI. That is simply the inverse of this. We want Ni by Si. We have now got Si by Ni, so that is what we want. So we want actually Ni by Si. So Ni by Si is simply the inverse of this. It is 1 by e power alpha plus beta epsilon I minus 1. Okay. So this equation that you get here, Ni by Si is 1 by e power alpha plus beta epsilon I minus 1, this equation that we have got here, this is the Bose-Einstein distribution, and we designate it also by F with subscripts Be. This tells you for every given energy level what is the probability of occupancy of a state at that energy level. Okay. So this is what it is. Again this can be this alpha and beta can be interpreted as in terms of the chemical potentials of the system and so on. So that is not something we are immediately interested in, but this is the form of the equation that we get. This is the Bose-Einstein statistical distribution. So when you look at phonons, you look at photons, you look at Cooper pairs, they are as long as they are to the extent that they are they are bosons, they are classified as bosons, they are following the Bose-Einstein statistical distribution, which is here. Okay. So through this course we have actually looked at 3 statistical distributions. One was the Maxwell-Boltzmann distribution, okay, and that basically was that we got we could write it as P equals P of E equals some P naught e to the power minus Ei by kBt. If you just write it in the denominator, it will be e power Ei by kBt. Okay. So this is the Maxwell-Boltzmann distribution. This applies to classical particles. We also got the Fermi-Dirac distribution. This works for fermions, so electrons would classify as fermions. There we got f of E, okay, is f of E is 1 by 1 plus e power E minus Ef by kBt. Okay, so this is where Fermi energy and so on we had there. So this is what we got, and now we have got the Bose-Einstein distribution. So f of so we will call this FD for Fermi-Dirac, and this is Bose-Einstein, and that we have simply got as 1 by 1 e power alpha plus beta epsilon I minus 1. So this is essentially a plus 1 and this is a minus 1. So so these are the 3 distributions that we have got. And I mean, if you didn't know, only when you plot these up you realize that they are very different, and or when you realize the kinds of assumptions that have gone into them, they look very different. Some vague similarity is there in terms of how they lay out, but there is a big difference in how they behave in actual behavior. And in fact, in a sense, this is the Maxwell-Boltzmann distribution is considered the extreme approximation of these two. So under the right kind of conditions, these kinds of particles would actually reduce to looking like classical particles under the right kind of conditions, but in general these are separate sets of particles. Okay, so they are very distinctly different in how they behave, how they are distributed across energy, and therefore what you can expect from a system consisting of particles of any one kind when they are subject to certain experimental conditions. Now we have spoken about the Bose-Einstein distribution because we have already encountered 3 bosons in our discussion, and there are some peculiarities of it about of these bosons which is what we will familiarize ourselves with. As I mentioned, the Bose-Einstein distribution, since it consists of it is addressing a set of particles that are displaying quantum mechanical behavior but are exempt from the Pauli's exclusion principle, there is no limit to the number of particles you can place in a given state. Okay, so it turns out that given this basic idea, if you actually go to very low temperatures, you can expect that all the particles will keep going to lower and lower levels of energy and in fact can condense to a single state. Okay, so can condense to a single state. This kind of situation where all the particles in the system actually settle down to a single state at very low temperatures is called a Bose-Einstein condensate. Okay, so this is called a Bose-Einstein condensate. So as you go to very low temperatures, the particles will settle down to a single state, and that is called a Bose-Einstein condensate. Now the beauty of the Bose, there are several things that are very nice and interesting about the Bose-Einstein condensate. The first and I would say the most startling thing about it is this was predicted in 1925. Okay, so when the Bose-Einstein statistical distribution was written down and introduced to the world, at that point this the possibility that such a thing could occur because of the fact that it is allowed in that system, that was propounded by Bose and Einstein. So this is called the Bose-Einstein condensate. It was predicted in 1925. For a very long time after that, experimental facilities were not available to enable people to investigate those bosons at those very low temperatures. People were unable to investigate these bosons at extremely low temperatures to see whether or not such a condensate forms. So this was predicted in 1925. Only 70 years later, in 1995, okay, 70 years after the prediction was made that such a state of matter could exist, it is considered as a new state of matter. 70 years after it was predicted that such a state of matter could exist, in 1995, in a collection of rubidium atoms, it was shown that when you go to very low temperatures, when you talk of very low temperatures, please remember this is not already talking of 2-3 Kelvin is very low temperatures, but where they are in this kind of an experiment, they are talking in terms of 10 power minus 7 Kelvin, extremely close to absolute zero. It is a huge experimental achievement to even get a experimental setup where you can reach this temperature. Okay, so this it is not a simple thing to reach this kind of a temperature. It is a phenomenal piece of work to reach this kind of a temperature. And in 1995, a group scientists were able to actually accomplish this temperature with and subject rubidium atoms to this kind of a temperature. When they did that, they were able to create this condensate. Okay, so they created this Bose-Einstein condensate for a set of rubidium atoms. For doing this in 1995, the 3 people involved, who were Cornell, Wyman and Kettle. Cornell, Wyman and Kettle, they got their Nobel Prize in 2001. They got a Nobel Prize for accomplishing this in 2001 for something that they did they managed to do in 1995. So till 1995, 70 years after this state of matter was predicted, nobody was able to accomplish this. With a lot of difficulty, they managed to reach this kind of a temperature, this group, these scientists, and they were able to show in 1995 that this condensate actually exists, that it can actually be formed. Okay, and for that they got the Nobel Prize. The point is that in fact, if you look at it, for example, that I would like to point out a couple of things here. One is just a matter of historical interest. and a sort of reflection of how sometimes things work in science. Bose-Einstein predicted this in 1925. 70 years later somebody managed to actually show it. For doing this they got a Nobel Prize, but strangely enough Bose was involved in all this and was very instrumental in this. It was his original idea. Strangely enough he never got a Nobel Prize for his work. Okay, so Satyendranath Bose somehow missed getting a Nobel Prize, but people who later proved his prediction to be correct actually got a Nobel Prize. So that is one of the strange things about science, and I just wanted to point that out. The other thing is actually when you look at this kind of a temperature, I think it is important to understand what this represents. Okay, so if you see when we spoke about black body radiation right at the beginning of our course, and through the course we have touched upon it on a few occasions, black body radiation. If you look at the universe around you, people have done experiments, and I mentioned this earlier, where you can look at the background radiation in the universe. Based on the background radiation in the universe you can say what is the current temperature of the universe. Okay, the current temperature of the universe is of the order of 2.7 Kelvin. Okay, so 2.7 Kelvin is the background temperature of the universe. The current understanding of the universe is that it started off at a very high temperature and then it has been cooling steadily. The Big Bang theory that we talk of effectively implies this kind of a situation with respect to temperature. Extremely high temperatures were there in the first nanoseconds after the universe was formed, and ever since it has been cooling, and what you have this background temperature that we are talking of is the current background temperature of the universe. Okay, so that is, in other words, this is how cool the universe has become. Anything else in the universe is only hotter than this. Okay, nothing in the universe in the sense of naturally occurring parts of the universe. Okay, whatever has occurred naturally in the universe over time has been cooling steadily, and this is the temperature that we have in the background. Okay, so whenever you are doing some experiment in the lab, if you manage to reach a temperature lower than this in your experiment, if you go to a temperature lower than this, which you will be doing artificially, okay, you are doing using some compressors, you are using some pumps, you are using something else, you are using much more sophisticated equipment were used here. They used all sorts of different means to slow down atoms, because the energy of the atom is effectively its temperature. So they used very interesting methods to slow down the atoms and get them and effectively lower their temperature. So whenever you do this complicated thing, you are doing it artificially, you are imposing it on the system, you are sort of forcing the system to undergo all those things. So whenever you drop below this temperature, in a sense you are dealing with a situation that does not naturally exist anywhere else in the universe. Okay, that is a remarkable statement to make. Okay, to say that in my lab I have an experimental situation which is not naturally occurring anywhere else in the universe, that too we can say with confidence is whenever you are doing this kind of a thing. If you are going to higher temperatures and higher pressures, invariably you will find something in the universe which is having that kind of a temperature or pressure, but to get it to below this point you are already talking of something that does not naturally exist anywhere. I mean, to the extent that if it exists anywhere else, chances are that means there is intelligent life elsewhere which is managing to do the same kind of experiment. The fact that you are actually able to accomplish this in the lab means you have done something that nature has not yet accomplished of its own accord in the universe. Okay, and this is just 2.7 Kelvin. We are talking here of 10 power minus 7 Kelvin, which is remarkably lower than this. And as I mentioned, you know, in material science and metallurgy and so on, we talk of temperatures say from say minus 100 degrees C to a few thousand degrees C. That is a range of temperatures that we routinely access. We do not think too big about it, we just routinely access that scale of temperatures. But if you drop from about minus 100 degrees C to minus 273 degrees C, which is what this 0 Kelvin is. Okay, so that is only about 173 degrees centigrade, right, or of the order of say, if you can even go to a narrower window of the order of say 100 Kelvin. Liquid nitrogen will get you to about 77 Kelvin. So from there if you want to drop down, it starts getting more and more difficult. So liquid helium will get you, liquid hydrogen, liquid helium will all get you into that 10 Kelvin or thereabouts, right. So from there to drop down to 0 Kelvin, the last 10 degrees starts getting to be very, very difficult. It is not easy to get you down the last 10 degrees. Certainly as you start dropping into the last few degrees, it's a remarkable piece of work to get to that kind of temperature. That is the reason it took 70 years to go from whatever was predicted to actually demonstrated in the lab. Simply not being able to cool a system down to that temperature, that was the experimental difficulty. So you talk of, you know, highly sophisticated experiments and whatnot. This is a highly sophisticated experiment, but what were they doing? They were simply lowering the temperature. That is the basic that is the fundamental thing that they were doing. There were of course lot of other things that they were doing, but that is the fundamental thing that they were doing, lowering the temperature. So lowering the temperature is itself a very phenomenal experimental accomplishment. Okay, so in this process they were able to show the Bose-Einstein condensate. So to sum up, today what we have seen is we have looked at bosons in much greater detail. We have looked at the conditions that are relevant to the particles that are classified as bosons. We have looked and we have used those conditions and looked at the distribution across energy levels that the bosons will demonstrate. Okay, and so we have therefore worked our way through the Bose-Einstein statistical distribution, and we see we have also briefly seen how it looks with respect to Fermi-Dirac statistics and Maxwell-Boltzmann statistics, and we have also looked at this phenomenal and very interesting scientific feat of some prediction that was made in 1925 and then experimentally proven 70 years later in 1995. So with that we will halt today. This sort of covers our discussion on the bosons, and it sort of relates to all the other things that we have discussed in the last few classes. So we will halt here today at this stage, and we will pick it up in the next class as we will look at just a few more interesting points before we wind up this course. Okay, thank you.